If the following statement does not make sense, go back and watch the Unit 1 video entitled Transformations of Variables. Recall, if we know the mean and standard deviation of a variable, multiplying every score in the population by a factor of a affects both the mean and the standard deviation. Both parameters are multiplied by a. But if a term b is added to all the scores, only the mean is affected since the scores all shift over but are no more spread apart. Hence, here are the formulas for linear transformations of a random variable. It is called a linear transformation because ax plus b is like mx plus b. Here's how this looks in an example. The coffee shop has a very expensive blend of coffee. It sells it for $2 per ounce plus a $1 charge for a special bag that preserves its deliciousness. Describe the distribution of the selling price of a regular size bag of this special coffee blend. Converting this normal distribution of weights in ounces to price in dollars requires us multiplying all randomly selected bag weights by 2 to convert from the weight of the bag of coffee to the selling price, and then adding the $1 charge for the special bag. Thus, our linear transformation, not a joint distribution which combines multiple bags, is 2x plus 1. The mean weight is multiplied by $2 and the $1 for the bag is added, converting the mean from 12.6 ounces to $26.20. The standard deviation is only affected by multiplying ounces by $2 per ounce, widening the gap between scores and the mean. But all scores have $1 added, so they all slide up by $1 and are no more spread out than before. Thus, the standard deviation converts from 0.4 ounces to $0.8, which is 80 cents. Before you practice more linear transformations, let's compare the joint distribution of x plus x to the linear transformation of 2x. Returning to the problem we just did, let's eliminate the $1 charge for the special bag. 2x would be the price per bag because we're going to be charging $2 per ounce. Notice that the standard deviation is merely 2 times what it was before, but the sum of weights of 2 randomly selected regular sized bags has the same mean, but a different standard deviation from the linear transformation. It seems like x plus x should be equivalent to 2x, but it's not. X plus x selects 2 bags, it's a joint distribution. 2x only selects 1 bag and doubles it. With x plus x, the first bag might be a heavier one, but there's then a reasonable chance that the second bag will be a bit on the lighter side, so the sum will not be too far from the mean, the expected sum of weights of 25.2 ounces. So why would the linear transformation have a larger standard deviation? It's because we'll only select 1 bag. If that first bag is heavier, we will not select a second bag likely to temper the extreme weight of the first bag. Instead, we will simply double the weight that we got. This allows us to get some results a lot further from the new mean of 25.2. And this is why we need to calculate the standard deviation for joint distributions of x plus x by taking the square root of the sums of the variances, while calculating the standard deviation for linear transformations by just multiplying the original standard deviation by the factor of 2. The standard deviation is larger in the case of the linear transformation for which only 1 score is selected, and that score can be extreme.